Okay. Hi, everyone. Thank you to ARCS for having me here. And I will be talking about the work that I did during my PhD at IIT Bombay. I will be presenting about my work, which is about learning language processing models with limited label data through efficient supervision, data transformations, and specialized architectures. So I started my PhD at IIT Bombay roughly around the time when BERT, a self-supervised learning model from Google, was introduced. And since then, there has been a dazzling progress in the field of machine learning and natural language processing. We have, thanks to large-scale self-supervised pre-training, we have gone from transformer models containing millions of parameters trained on billions of tokens to transformer models trained on billions of parameters and containing billions of parameters and trained on trillions of tokens. However, throughout this rapidly evolving landscape, one thing that has remained constant is the requirement of high quality human annotated data sets. For instance, the Llama 3 language model that was introduced last year was fine tuned on 10 million human annotated examples despite being pre trained on 15 trillion tokens. However, we all know, all the practitioners know that obtaining high quality human annotations is very challenging. It requires hiring annotators in the first place and establishing various practices and processes to ensure data quality and data diversity. And because human labeled datasets are so precious, my thesis focuses on how to learn efficiently with limited human supervision. So we consider three main directions. One is how can we collect more effective supervision under limited data annotation budgets. The second is how can we generate high quality synthetic data. Again, a very recent and very hot topic. However, my research takes a different view that for most of the data sets, you have related data sets already in existence. And you can transform these data sets carefully using language models, and you don't need to generate synthetic data from scratch. And transforming existing data sets kinds of also provides you the natural diversity that exists in naturally occurring data sets. The third direction that we take is building efficient architectures with task-specific priors. So suppose you want to build a model for a specific task, and you have only limited amount of labeled data. We demonstrate that if you can somehow build task-specific priors into these model architectures, for example, we show for the case of grammatical error correction, here our work was used by Grammarly, and for the tasks of text-to-SQL parsing, integrating task-specific priors into model architectures provide better accuracies for a limited amount of labeled data. So let me dive into the first part of the talk, where I will be talking about how to collect efficient supervision under limited annotation budgets. So typically for classification tasks, human annotators are only asked to provide ground truth labels. However, human annotators can provide more richer forms of information, and our work considers asking human annotators to let them generalize their examples into rules. For example, if a human annotator is trying to label product reviews into positive and negative, they can easily come up with a rule that if a review contains words like highly recommend, the review is likely to be positive. So rules, although asking for rules can incur a little extra cognitive effort to the annotators, rules can in turn be used to noisily annotate thousands of unlabeled instances. And this kind of allow annotators to label many instances in a single shot. However, there is a challenge. Rules can often be noisy. For example, if a product review contains highly recommended, it may not necessarily be positive. And the opportunity lies here is how to learn from such large-scale, noisily labeled data sets. So the approach that we take is to restrict, we try to restrict rules to the regions where they are correct, and we try to suppress rules in the regions where they are incorrect. So in order to identify whether a rule J has correctly fired on an instance I, we introduce a random variable RJI. RJI is 1 if rule J correctly labels instance I. And this kind of also provides us a logical constraint over variables RJI. So RJI equals to 1 implies yi, the true label, is same as the rule assigned label. And we model probability of coverage variable RJI and probability of the true label yi given xi using neural networks. And this logical constraint can be turned into a soft form by plugging in these probabilities out from neural network outputs. And so this logical constraint can be expressed in soft form by plugging in the probabilities, and the negative log likelihood of satisfying this logical constraint is what we apply on the noisily labeled instances. And this allows us to suppress rules in noisy regions. So one intuition here is if the probability of coverage variable is very high, this implication loss, the negative log likelihood of the constraint, is same as the cross entropy loss, essentially treating the rule labeled instance as a clean instance, the correctly labeled instance. And if the probability of RGI is low, which is the network thinks instance J is not correctly labeled, implication loss is close to zero, essentially withdrawing the instance from training. And in this way, we are able to learn from noisily labeled examples by only focusing on examples that are clean. So we compared our work with a battery of methods that existed at that time, which focused on learning from rules and learning from noisily labeled datasets. And across 5 tasks, we found that our method provided consistent gains over a simple baseline of just training on the annotator provided labels and completely ignoring the rules. So all other baseline methods do make use of noisily labeled datasets. And the main reason, we found that our method particularly worked well when rules are noisy, and rules are going to be noisy in practice, and also particularly when the size of labeled datasets is small. So our method consistently outperformed when we had very limited amount of labeled data. And the main reason why our method works better is for its ability to denoise rules. So in this graph on the right, on x-axis we have different data sets. On y-axis, the green bar represents the original precision of the rules provided by human annotators. And in the red bar, we have denoised precision, the new precision of rules after we have suppressed them in the noisy regions. And this provided us much cleaner supervision, allowing us to learn more accurate models. So, funnily, one of the ICLEIR reviewer thought that our work could potentially trigger a paradigm shift in many research areas of machine learning. And our work indeed had a significant impact, with many well-known research libraries and papers building on top of our code and datasets that we had publicly open sourced on GitHub. Particularly Wrench benchmark developed by Snorkel company, which is very well known for its data programming solutions and weakly supervised learning methods, made use of our datasets and code. Other projects that used were from Microsoft and an independent project from IIT Bombay. So I just talked about how we can collect more effective supervision under limited annotation budgets. We'll now see, suppose you don't have enough budget to collect labeled data. One common way is to generate synthetic data using language models. But one interesting observation is, in many settings, labeled data often pre-exists in related contexts. So for example, if you want to build a model for a specific task, for Hindi or Tamil language, you might often encounter a dataset solving similar tasks but in English. So you can always transform datasets from one language to another. And we also show that not just translating datasets from one language to another, we also propose methods to transform the domain of the datasets from one domain to another. So for example, if you already have question answering datasets in English, if you already have question answering datasets for cricket, you can carefully alter question answering datasets for cricket to create question answering datasets for a low resource domain like hockey. So I will dive into how we created bootstrapped semantic parsing datasets for 50 diverse languages using large language models. So semantic parsing is a very simple task where you have input utterance, like create an alarm for 8 a.m. And the task is to parse this utterance into actionable logical form, like which contains an intent, like create alarm, slots like date time, and slot values or slot arguments which are grounded in the utterance, like 8 a.m. So think of it as very simple text to API calling task. And a common way that existed was to translate the utterances using production grade machine translation services like Google Translate. However, production grade machine translation services can only give you the translation of the utterance, but we also need translation of the logical form, which contains slot values in the target language. And this required prior methods to separately develop models, which is labeled as slot filler, in addition to the production grade machine translation service, to also generate translations for the logical form. Now, language models made almost everything easier. The pipelines were very simpler. So we also wanted to see how well language models can help us translate semantic parsing datasets. And for this, we assume very small seed set of examples from English to a target language, translations of both utterance and logical form pairs. And we use these seed examples to prompt the language model to translate rest of the training data in English to a target language. And during translation, we not just generate one translation, we sample multiple possible translations of a given example. And we also employ some quality filtering techniques to discard inconsistently translated examples. A benefit of this approach is we don't need separate modules for translating logical forms. And we can also generate translations, in-domain translations through in-context learning. However, a challenge here was that, in fact, till date, production-grade machine translation services are known to be far better than off-the-shelf large language models in translation. So in this figure, although bars may not be clearly visible, it shows that for low-resource languages, a service like Google Translate is much better than off-the-shelf GPT-4 or ChatGPT. So even though we were using language models, the models trained on datasets generated using our method provided much superior accuracy gains over prior state-of-the-art method that used production-grade machine translation services. So on x-axis, we have different languages. On y-axis, we have gains of our method over a prior state-of-the-art which used machine translation service. Now, this was a surprising result because, as I just showed, that production-grade machine translation services are actually better. Then why are datasets translated using language models giving us better downstream accuracy? So the main ingredient that allowed us to achieve better performance was generating multiple samples for multiple translations for a given example and filtering out inconsistently translated examples. So on x-axis, you have different languages. Green bar shows a result with generating only one translation per example. With 8 samples, we get additional boost in accuracy. And the most important takeaway was if you are somehow able to filter inconsistently translated examples, that provides us even better results. So an opportunity for future research is that manually translated datasets. So if we replace machine translated datasets with human translated datasets, they still continue to provide better accuracies. And future research would be how we can synthetically generate translated datasets that are closer in characteristics to these manually translated datasets. So far, I have been talking about data-centric methods. How can we collect more effective supervision under limited annotation budgets, or how we can generate synthetic data, high-quality synthetic data. The last part of my work is more model-centric. So given a labeled data set, how can you integrate task-specific priors into the model architecture to achieve better, more accurate models? So I would specifically like to highlight my work on grammatical error correction. So when we started this work, grammatical error correction was seen as a translation problem, going from incorrect English to correct English. And all the state-of-the-art models for translation systems were used. For example, encoder-decoder models. They would take an input sentence. For example, okay, sentence is not visible, but sentence is, she saw Tom is crashed by a policeman in park. And generating the correct sentence token by token entirely from scratch. We thought this is very redundant, wasteful, because whenever you are trying to fix errors in a grammatically incorrect sentence, you don't need to generate entire sentence from scratch. All you need is a few local edits like punctuation errors, article errors, and verb forms. So we designed an entirely new architecture tailored for grammatical error correction, where instead of generating entire corrected sentence from scratch, token by token, we would parallelly edit all the tokens in a single turn. So, for example, given the input sentence, we would generate edits. So, for example, replacing cached by caught, appending article or to by, appending in with the. So our output vocabulary is now not tokens of English language, but edits like insertions, deletions, replacements, or just copy the same token in the output. Now, there are several benefits of this method. One is because we are doing everything in parallel, it is extremely fast compared to generating output token by token. Our output space is much smaller, making the task easier to learn. So instead of training output vocabulary of 30,000, we were only considering 2,000 most common edit operations that covered roughly 85 to 90% of errors in the data sets. And this also allows us to be more precise because our edit vocabulary is small, so model is less likely to hallucinate. So in terms of accuracy, we were able to match accuracy of state-of-the-art models published by Google at that time. But even more importantly, our models were 15x faster compared to state-of-the-art models at that time. So in this graph, we have on the lower two lines are our models, and the BERT small and BERT large, and on top, the two lines are state-of-the-art models from Google, which were similarly sized but much more slower. So I presented this work back in 2019 at EMNLP, and one of the Grammarly researchers came by our poster, and they were very interested in our method. Eventually, in 2020, they ended up re-implementing our method, and they were not just able to reproduce our results, but with some hyperparameter changes, they were able to achieve better results. And yeah, so as per quoting a Grammarly researcher, they felt that our idea was a proper idea for production. So that's a summary of my PhD thesis contributions. My PhD thesis contributes methods for learning language processing models with limited label data through efficient supervision with by reducing annotator effort, generating high-quality synthetic data using data transformations with language models, and developing efficient architectures with task-specific priors. We consider a wide variety of applications ranging from semantic parsing, text-to-SQL, accented speech recognition, grammatical error correction, machine translation. Most of this research is available as open source on my GitHub. And in the end, I would like to conclude by thanking an amazing set of mentors and collaborators at IIT Bombay and various other places. I'm particularly grateful to my advisor, Professor Sunita Sarafgi, for giving me this opportunity. It was a very good learning opportunity, and if there are students here, I would highly encourage you to join IIT Bombay for a PhD. I had an amazing experience there. With that, I would be happy to take any questions. Thank you.
Okay, are there any questions?
First of all, congratulations for your work. I would have a lot of questions, but let's just one on the second area of your research, which is this translation. Okay. Now, all your work translated from English to other languages, but somehow I feel, being Italian, that English is much simpler as a sentence structures compared to the Italian language, where a sentence can be an entire paragraph. So when I translate from Italian to English, I have to think how to split this Italian sentence in multiple sentences in English. So I wonder whether the techniques that you propose would be effective when you translate for a language, the very complex sentence structure, to English, which is simpler.
Yes, so that's a good point. However, what happens to be the reality is for most of the tasks, data sets are only available in English. So for many tasks, data sets are only available in English, and hence we want to go from English to other languages. If there are data sets that are available in other languages and we want them in English, the same technique should work as it is.
You don't work on translating the actual language, just a data set.
Yes, so we are translating entire data set rather than just utterances.
So it wouldn't work for general translation tasks.
Sorry, I didn't.
So it wouldn't work for general translation
Um,
tasks.
So people have evaluated it for specifically for translation tasks, and this is what they find. They find that like dedicated machine translation services like Google Translate are still better than off-the-shelf large language models, particularly for low-resource languages.
Yanis?
I think my question is naive. You talk about translating data sets, and I'm a data guy, and I'm used to having schemas. And one of the biggest problems in data management is data integration, schema integration, I mean schema matching and so on. I think I know the answer, but I want to hear. Can this be elevated one level up of abstraction and be used for data integration and data harmonization, not data, I'm sorry, schema harmonization tasks?
So I'm not very familiar with data integration, but for example, if you are trying to build question answering model for relational databases in English, you have a schema. Now, do you mean we want to build a similar model in?
We have the schema for a hospital in Coimbatore, the schema for a hospital in Delhi, and one in Tokyo. And they have similar kinds of data, but the schemas are quite different.
Okay.
Because they use different terminology, different conceptions,
Yes.
and so on. Can we use this to map from one schema to the other?
No, so this is purely meant for going from one language to another language. It's not meant for like translating schema. However, we had one more work that I did not present here. So, for example, if you want to go from football to university, if you want to go from one domain to another domain, they might have different schemas, but we can do something here to carefully morph examples from one schema to another schema. But I'm not fully sure if I still get your question.
I think this is, I mean, I'm talking about mapping from one hospital to another.
Yeah.
Schemas, going from football to, what was that?
University.
Is even more unrelated. So
Yeah.
if this works, then the other one should work as well.
Yes, probably.
Because semantics is also a type of language. So that's why I thought, but we can talk offline.
Thank you. Thanks.